Intelligence is information that has been processed, exploited, and analyzed to project future events and reduce uncertainty, giving decision-makers a concrete advantage. Historically, intelligence apparatuses were built for environments of extreme data scarcity, where the objective was to find a single, high-value signal hidden by a monolithic adversary. This scarcity-first mindset was institutionalized with the National Security Act of 1947, which established a permanent structure of compartmentalized intelligence agencies. This established the legacy intelligence cycle, known as TPED: tasking, processing, exploitation, and dissemination. This linear, stovepiped process functions securely because the signals being sought were exceptionally rare and difficult to acquire. Today, that environment has inverted. Open-source intelligence now accounts for 80 to 90% of all collection, shifting the landscape from scarcity to overwhelming abundance. Legacy intelligence cycles fail because the primary challenge has moved from locating a specific secret to managing a state of permanent data saturation. When management philosophies designed for scarcity meet high-velocity digital data, the result is a swarm ball. Analysts become paralyzed by noise. This creates a fatal awareness gap, where information exists in the system but cannot be translated into cross-domain response. The result is a widening warning response gap. Intelligence fails to trigger an effective policy response because the system can no longer provide sufficient lead time. Survival in this environment requires temporal parity, the operational capacity to process and analyze intelligence at the exact velocity the adversary generates it. While temporal parity demands automated frameworks, the resulting speed introduces algorithmic vulnerabilities that require a new type of epistemological shield. To achieve this speed, organizations must transition from restrictive need-to-know models to decentralized trusted networks driven by a responsibility to provide. Scalable automation is realized through the Integrated Threat Intelligence Mining and Extraction Framework, or INTIME. The first layer uses automated harvesting via support vector machine classifiers to prioritize topically relevant data at the point of ingestion. Natural language understanding then autonomously extracts and ranks domain-specific entities, such as malware samples or malicious shell commands. This produces instantaneous, machine-readable intelligence, standardized through STIX and TACACEE formats for rapid sharing across the enterprise. This framework clears data smog, recapturing thousands of engineering hours from cognitive toil and closing the warning response gap. However, high-speed automated ingestion creates a massive attack surface for silent algorithmic manipulation. Pursuing technological speed without structural integrity leads to epistemic failure. The architecture requires a built-in philosophical security layer. Adversaries exploit these automated pipelines through data poisoning, embedding invisible, sample-specific triggers to manipulate machine learning predictions. Attempting to exhaustively verify massive open-source datasets is a losing strategy that favors the adversary's ability to generate deception. The solution to this vulnerability is found in Karl Popper's theories of deductive falsification. Using the refutation method, systems do not try to verify every data point. Instead, they actively seek the single refuting contradiction within a synthetic narrative. This refutation is formalized across computational hierarchies as mismatch logic. The system triggers an alert the moment an extracted entity contradicts a known baseline of truth. This logic is physically coded into the ingestion pipeline through Security Machine Learning Operations, or SecMLOps. SecMLOps uses provenance tracking and adversarial training to neutralize hidden backdoors before they ever reach a human analyst. This acts as an epistemological shield, turning the adversary's volume strategy against them by mathematically increasing the probability that logical mismatches are caught. These principles are operationalized through the Center for Applied Cyber Epistemology and Emulation, CACEE. The secure in-time and SecMLOps pipeline forms a foundational enterprise single source of truth for the entire ecosystem. Layer 1 is Tradecraft Education, a scalable academy where industry professionals learn to synthesize raw data into verifiable intelligence. Students use ephemeral, containerized Google Cloud workstations that provide a safe sandbox for cyber-physical attack emulation against dummy infrastructure. Layer 2 consists of tabletop exercises, high-impact consulting for public-private partnerships in the water, power, and transit sectors. These exercises measure how effectively the C-suite and engineers share facts and maintain a shared reality during a crisis. Layer 3 is the Information Sharing Network node, which transitions the center from a consumer of intelligence to a validated producer. Notebook LM acts as a dynamic white cell controller, injecting real-time variables from the single source of truth into live simulations. Using a federated API gateway, trusted industry partners subscribe to vetted sticks and taxi feeds curated by the center. By anchoring simulation and education in Popperian security, these layers provide a verifiable framework for processing and sharing truth across the cyber-physical sector. The CACEE architecture connects intelligence, training, and operations into a continuous reinforcing loop. This is the wisdom internalization-externalization feedback loop. The loop begins when an industry professional learns a specific tradecraft concept in the academy. If that professional struggles with a technical step inside their cloud workstation lab, the system captures that telemetry. This friction telemetry is fed back into the single source of truth and the Notebook LM exercise controller. The system automatically updates the curriculum and triggers new targeted content addressing the specific pitfall. This content drives new, highly qualified users back into the academy, where the process repeats. This architecture standardizes the mechanics of social epistemology directly into the cyber-physical operational space. CACEE represents a self-sustaining supply chain that transforms raw data into intelligence, intelligence into resilience, and marketing into monetized education.